Welcome back to ECE 320A. Forgot which class I was in. Sorry. 320A today. Homework number 6 is due next week, and I hope to have some convolution material for you to look at if you want to prior to class next time. Look at in Unit 7 on D2L, but you should have access to homework assignments 6, 7, and 8, which are the homework assignments that will be due prior to exam number 3, which isn't too far around the corner. Today, what I want to concentrate on will be incorporating initial conditions into S-domain circuits, and we really have two ways that we can do that. We can either introduce those as series voltage sources or parallel current sources. And which way we decide will probably depend on how you are planning to analyze that circuit or perform the analysis. Whether you're going to do mesh analysis or node voltage analysis will influence how you decide to incorporate your initial conditions on these energy storage elements. And we'll derive those or show where those come from. Then we will actually get into a very important topic, not only to this course, but to many future courses in the curriculum or in your future, and that's this concept of transfer functions. Basically a rational expression that relates an input to an output. And we'll try to start illustrating that by means of finding a system's response, system's output response. What is a system's impulse response? And once we know a system's impulse response, we can then find the output due to any crazy input waveform by means of convolution. And that's where convolution comes into play. We can also use the transfer function to find the sinusoidal steady-state analysis or the sinusoidal steady-state response, the output given a sinusoidal input. If that's the case, if we're doing sinusoidal steady-state response, how long do we have to wait before we are in a sinusoidal steady state? 5 tau. And it depends then on how slow your slowest tau is, but in an electrical system, tau is not very long, and 5 of those isn't very long, and so you're waiting that length of time, and then you're just sitting there moving at the frequency, the sinusoidal frequency of your input waveform. We're assuming we have linear circuits, and so that's why we have this transfer function. We can also talk about transfer functions based on a filter. We can have a filter's transfer function. Here's a low-pass filter. Here's a high-pass filter. Here's a band-pass filter. Here's a notch filter. All of those have a transfer function, and we can then analyze or think about those transfer functions or those filters based on this transfer function. Obviously, that means that if we're talking about different frequency response behaviors of a system, we might want to know what is the system's frequency response, and that's a Bode plot. And we'll talk more about that later, but that's also something you can be looking at, which is in Appendix E, I believe, of your textbook. And then, if we have time, we'll start developing the convolution integral. Let's now remind ourselves initially of what we talked about last time, but let's now consolidate all of this into the two different options or two different ways that we can model initial conditions that arise from energy that's stored in an inductor or in a capacitor. Or how do we incorporate initial conditions into S-domain circuits? And it all sort of revolves around Eli and ice. You're probably tired of me saying Eli and ice, but hopefully if you now hear Eli, oh, hello, my name's Eli, you're going to go, V is equal to L d I dt, just instinctively. That's fine. You might not want to say that when you're shaking his hand, and then when you meet Mr. Ice, the same thing will happen, right? I is equal to C dV dt. May even have some rap music playing or something. I don't know. We now have the inductor. This relationship in the time domain is what you can see or think about or immediately write down. V is equal to L di dt based on this mnemonic Eli. That's why we're saying Eli and ice, just to give us a way to remember the current voltage relationship of these two energy storage devices. Eli for an inductor, since Eli contains an L, there's your inductor. Ice contains a C, there's your capacitor. But we're using the passive sign convention. The current through that inductor is going into the end of that inductor that we've now labeled with the positive polarity marking. And if that's the way that we've labeled the inductor, then we know that the inductor voltage is proportional to the time rate of change of the current through that inductor. And the proportionality constant is the inductance value L. Last time we said, oh, if we have it in the time domain, can we take it into the frequency domain? Can we Laplace transform the time domain equation? You know how to Laplace transform a derivative. And the correct answer is up and down with the, in the United States, it's up and down. In other countries, it might be this. But we're here in the United States. In the kitchen or living room, I forget which one we're in with when we're in the frequency domain. But now we have L times the Laplace transform of the derivative of the current, which is now the product S, the frequency variable S, times the Laplace transform of I sub L minus the initial condition on that initial, or the initial condition on that inductor, and that I sub L of 0 minus is the time domain value of that current going through that inductor from left to right, the way that we've labeled it, and we're subtracting it, and that is all based on Laplace transform definition of a derivative. If we distribute that inductor, that constant, through both terms on the right-hand side, we can now collect S with L. S is a complex frequency variable, and the product SL, if you look at it through your Ohm's law lens, you can see that V is equal to, instead of Ri, now we're generalizing it to Zi. V is equal to Zi, where Z is the impedance of the inductor, that's SL, and I is the Laplace transform. What we're doing in addition to this impedance relationship or Ohm's law relationship is accounting for the initial condition. And that's this second term in this voltage expression for the inductor's voltage in the frequency domain or in the S domain. We're now summing up two terms to create a voltage. That's now going to immediately give rise to our S domain series circuit. Series meaning it's connected in a series manner, and if the left-hand side is the Laplace transform of a voltage, the right-hand side terms all have to be having the units of voltage. And that's where I can immediately sort of start taking points away when you were, and you did pretty good on writing the differential equations for a circuit, but sometimes I'll see voltages plus currents equal voltages. Your units don't match. You just get all hung up on, oh, I need this to be LDI, I need this to be CDV, and you just start writing things down, and you're actually adding and subtracting voltages and currents. Well, if you have an equal sign, the units have to match. And in this case, if the left-hand side says we have units of voltage, then SL times I must be voltage, and L times I sub L of 0 minus must be a voltage in the frequency domain. That's now the S domain series circuit of an inductor. And if somebody now wants the Laplace transform of the voltage across that inductor, you can't just isolate on that impedance's voltage drop. You have to incorporate both pieces. If somebody says, oh, what's the voltage in the S domain across that inductor, you have to include that initial condition term, unless there's 0 on the initial conditions. And what does a voltage source look like when the voltage across that it's supplying is 0? If you have 0 voltage being supplied by a voltage source, that looks just like a short circuit. It's supplying 0, and what has 0 voltage drop across it? A wire. Meaning, if you don't have any initial conditions in that inductor, you could replace that source with a short circuit. Or you now have that voltage source with I sub L of 0 minus equaling 0, or it's a 0 voltage drop. If you wanted to convince yourself that that polarity labeling on the voltage source was correct, or this plus minus and the current were going correctly in that S-domain equivalent circuit, you could simply write a KVL equation, which I'm trying to illustrate with the red dashed line. Suppose you look at this Laplace transformed equation up above and you subtract capital V sub L from both sides. You have 0 is equal to minus V sub L plus SI I sub L minus L I sub L of 0 minus. Now if you start at the unarrowheaded tail of this red dashed line, you're going into the minus V sub L terminal. You say minus V sub L, and now you have plus SL I sub L of S minus L of I sub L of 0, and we're back where we started, so it should be equal to 0. That's how to verify or validate the polarity in that series source. That's typically where students, I don't know, which one is it? Plus or minus? Where is it? Well, just do what you know has to hold. Write a KVL equation and validate. That's now the S-domain series circuit associated with an inductor that incorporates the initial condition. Suppose we wanted to do, and that's nice if you're doing mesh analysis or writing KVL equations in your entire circuit or in a particular branch that has that inductor in it. You might want to then incorporate your initial conditions as a series voltage source. Suppose you're writing KCL equations. You're doing nodal analysis. Then you say, I don't want a series voltage source. That just gives me another voltage to try to keep track of. I want to now rewrite or express my S-domain circuit of an inductor in a parallel manner. I want to now incorporate my initial condition as a current source, not as a voltage source. This first equation that I'm showing now at the bottom of the page, I simply divided all terms by SL and isolated on the current I sub L of S from the original formula here. If you simply add L I sub L of 0 minus to both sides and divide everything by SL, then you will end up with that equation. In this form, you can see that the current is actually equal to 2 currents. We have 2 component parts of this total current in our inductor. One of those parts of our current is due to an impedance. If you have V sub L divided by an impedance, that will now give you a current. And that now is V sub L over SL. You also have then I sub L of 0 minus over S. So let's now see if we can put that into an equivalent circuit. What would that look like? We said we had I coming in here. Or now I'm simply going to do a KCL equation at essentially that point. And I sub L is made up of two parts. I have one part that's associated with an inductance, with an impedance, and that I will represent as SL. And I have another part that's associated with a term, an additional term, which I'm just going to draw in as a current source. If I now apply KCL here, hopefully you can see that that's going to be I sub L of S, capital I sub L of S, equal to these two currents leaving that node. And the top one, if I now said, oh, my voltage across that inductor is right there, V sub L of S. The current is going into that positive node of that V sub L of S. And now if I have V sub L divided by that impedance, SL, I will get this current. Let me call that I1. The other current, which maybe I should have done, well, let me draw it blue in case there's problems distinguishing between green and red. That's just can be an issue for some. So now here's blue. That now needs to be this current, I sub L of 0 minus over S. And all of that now is obviously equal to what's coming out the other side. And now you have a parallel structure for incorporating the initial conditions on an inductor. If you're doing node voltage analysis, it might be more convenient to put in current sources instead of voltage sources. Realize that this value associated with this current source, I sub L of 0 over S, is obviously not the same as the label or the value of the voltage source. That was L, I sub L of 0 minus. No S involved. But they do both include the initial condition. Questions on those two different ways of incorporating the initial conditions associated with an inductor? Yes?
So, I guess from the use of parallel just to find voltage, and then you use the series to find the current throughout.
So now the question was, when, I think, I'll paraphrase this, when do we use which model?
Right.
And which model you use depends on the analysis that you're wanting to apply. Whether you're writing KVL equations or KCL equations. If you're writing KVL equations, you probably want everything in series. If you're writing KCL equations, then you probably want to use the last one that we talked about, which is this parallel current source model for incorporating the initial condition. So it really depends on what you're doing analysis-wise. If you do the analysis correctly, it doesn't matter which one you use, but it may make your job a little more difficult if you picked one versus the other. Meaning if you put this into a mesh, now you've just introduced an additional mesh. Why make your job more difficult? And in the other case, if you now had introduced a voltage source when you were doing node voltage analysis, now you just put in another node with a voltage you have to keep track of. Those are the reasons why you might use one or the other. Suppose we look at the capacitor. In the time domain, again, the passive sign convention, and ICE says I sub C is equal to C times the time rate of change of the voltage across that capacitor. That should not be shocking. Well, maybe it is if it was a supercapacitor and you touched it in the wrong way, but on this screen, it shouldn't shock anyone, okay? In reality, it could. It could be painful. That energy storage device. What happens when we Laplace transform? I'll do the hard part. I've Laplace transformed the left-hand side. I sub c of s. The other part is consistent with what we just had for the inductor. We have the proportionality constant, c, and now we have s, v sub c of s. Am I done? I could be if there was no energy stored in that capacitor. But if there is, if we do it as thoroughly as possible, then we have to subtract the initial voltage on that capacitor. Or now if we distribute that C across both terms, we now have SC V sub C of S minus SC V sub C. What am I doing? Making sure you're awake. Not distributing things very properly, am I? It's just the C minus C V sub C of 0 minus. You know why that happened. I just enjoy the S domain so much, I like to throw S's everywhere. Here's an S. Catch. But you now have S domain analysis. What's this look like, though? This may look a little bit odd because now we have some parameter times a voltage giving us a current. We can put that in the denominator, that SC. Well, we have to put it in the denominator of the denominator to make it consistent with that. Then it would look like we were dividing V sub C by an impedance to get a current. Or we can rewrite this. What I'm trying to say is V sub C of S over 1 over SC minus C V sub C of 0 minus. Where now what's in the denominator of V sub C is the impedance associated with that capacitor. And we can use the same thought process we used before to see what's happening with the parallel in this case, since we're starting with current on the left. Here's the parallel S-domain circuit equivalent for a capacitor, and you know how to write it. It's going to be I sub C, and then it's going to be made up of two pieces. One piece that is associated with the impedance, where the impedance is now 1 over SC, and the other piece is due to the initial condition. And how do we label, if I now say, well, this source, current or voltage, you tell me, is going to have a value of C, V sub C of 0 minus. Bless you. How do we label that source? First, what is it? Are we using plus and minus, or are we using arrows? We want it to be a current source, don't we? Since it needs to be consistent with a current. So we're putting an arrow. Now, which direction do we direct the arrow? Where's the head of the arrow? Left or right? It now is opposing. We'll just incorporate the sign in that minus CV sub C of 0 minus into the arrow direction. Or we're now saying that that now is going to the left. And that should be what we have there. I sub c is made up of two pieces, an impedance path and an initial condition path. And to see that, you could simply perform KCL at that node. Currents coming in equal currents coming out. What happens if we didn't want to do nodal analysis, we wanted to do mesh analysis, and we have capacitors? Then we need to find a series source representation or a voltage source to incorporate the initial condition. And we now know how to do that. Now, if this is the relationship, why don't we simply add C V sub C 0 to both sides and multiply everything by 1 over SC. And then we will have isolated V sub C of S. The voltage dropped across that capacitor. Or we now have the relationship or the equation V sub C of S is equal to 1 over SC times I sub C of S, and whatever is scaling the current must be the impedance. The impedance of a capacitor in the S domain is 1 over SC plus V sub C of 0 minus over S. In this case, the C's canceled and we're left with that one S in the denominator. And our circuit in the S domain looks like that. The impedance of that capacitor is 1 over SC. Let's say here is our current. If we need the complete voltage of that capacitor, we have to incorporate the initial condition. We can't just look at the voltage across the impedance. We have to make sure that we're including both pieces. And now this circle is going to have a value of V sub C of 0 minus over S. This is now V sub C of S. And you know the drill in terms of how to figure out how to label that polarity on the, you know it's a plus minus because it's a voltage. And you can say, well, here, let me perform a KVL again. I have minus V sub C plus 1 over SC I sub C plus, so now this is a plus, and that's a minus V sub C of 0 minus over S. We comfortable with this? How to incorporate initial conditions of energy storage devices, in particular the inductor and capacitor's energy storage with particular sources. To summarize an earlier question, let me just write down which circuit model, either a series or parallel, which circuit model is used in your analysis actually depends, here's what you're going to like, on personal preference. Doesn't depend on my preference, it depends on yours. It's however you feel comfortable analyzing that circuit. Well, it also might be influenced by the situation and the particular situation. What are some general guides? Suppose that you seem to see everything as a mesh analysis problem, then you might want to get very comfortable doing the series voltage sources. And it doesn't matter whether it's a capacitor or an inductor. You can create voltage sources, series voltage sources, to incorporate the initial conditions. Or if you wanted to do node analysis, then you might say, oh, I need to do parallel current sources. What you use depends on your particular situation, whether you want to do some nodal analysis or mesh analysis. You'll use either the parallel current sources or series voltage sources. We have just finished S-domain circuit analysis. Just saying. Woo! So now we get to apply it in many different ways, and the first way that we're going to be looking at it is to study something that's very powerful, and that's this idea of a transfer function. And a definition for that could be the following. Suppose I now say here is a transfer function, capital H of S. That really is, then, you could consider that to be the Laplace transform of some output time response over the Laplace transform of an input time response. This is now our transfer function. And why is it called a transfer function? Suppose you multiplied this H of S by the Laplace transform of an input time response. Do you see that basically the inputs cancel and you're left with the Laplace transform of the output time response? So the output time response, let's say Y of S, is equal to H times X of S, where X of S is the Laplace transform of the input time response. Here's the powerful piece. What H of S actually represents depends on, obviously enough, the input and the output. Depends on the input and the output. Why do I keep saying this is so powerful? Well, now you can abstract away a lot of analysis and just say, oh, my system is a transfer function H of S, and you can put it into a box. And now you can carry that box with you and say, I now have a transfer function, and it's of a filter. Somebody else says, I have a transfer function, and it's of a vehicle. I have a transfer function, and it's a filter. You can carry a lot of systems around in this box labeled H of S, where this is now our system. And you can now put an input into that, which we might call capital X of S. X times H yields the output Y. And the reason why you like carrying things around in that little black box that says H of S, or is a transfer function, is because now a lot of this analysis can be performed by multiplication, We don't have to do a lot of solving of differential equations in the time domain. Here's something that might confuse you a little bit. Suppose I hand you a circuit, and I say, give me the transfer function of that circuit. And you go, it depends. And I go, yes. It depends on what the input is and what the output is. We could have many, many different transfer functions for the same circuit. And that's what we want to illustrate right now. But one circuit, don't just think that one circuit means one transfer function. One circuit, depending on what it looks like, could generate multiple transfer functions. So one circuit or a system can have several transfer functions associated with it. So now let's look at some possible functions, or maybe I should say waveforms, that might be an input signal and one might be an output signal. So here maybe I should say example input and output signals. Maybe I'm missing or confusing you by calling them functions. Let's just say here's an input signal and here's an output signal, and what are they going to look like? Suppose that we now say, here's my column of inputs, and I'll label those as x of t in the time domain, and here's my column that I'll label output, and that now I'm going to give a label as a variable y of t. And now just let your mind go crazy in terms of what could possibly be in that input column. Since we're in this class, what are you going to say? Well, what's a signal? A current, a voltage. So we can immediately write those down. Those could be possible input signals. Now somebody goes, yeah, but I'm in this capstone with a mechanical engineer and he's worried about a force that's being applied. Or they're worried about the velocity of this device. Or they're worried about the angle. Or maybe the position. All of those could be x of t's. All of those could be inputs. You twist an angle. Here you could think of, Josie, I need an angle. I need an angle. And Josie, you know what Josie gives you? A potentiometer. She might give you a potentiometer. Now you can get a voltage, right, from that position or that angle. What could be an output? Now you don't even have to get creative. You can just copy down the left hand and say, well, that could also be considered an output. Right? So now we could say, oh, you know what? I'm just going to copy this that's on the left. I have a current. I have a voltage. This could be my y of t. I could have a force. Actually, if I applied a force to a mass, I might have Newton around and he might give me an acceleration. Or, yeah, Isaac might be with us. So now we have an acceleration. You know, I need to be, no, I don't. Anyway, velocity, angle. So I snuck one in on us, didn't I? I added an extra one, but we could measure acceleration. You guys probably have wearables that are measuring accelerations. You have accelerometers that tells your paces. right? It gives you this bump every so often. So now how many steps do you have? 2,000. I need to get it up to 10,000 before I can go to bed. So I'm pacing. I don't know if anybody saw that, but I just got a bug out of the air. Hopefully nobody... There's a piece of gum in that garbage. It stuck to the gum. No. All right. Somebody, that's even better than he pulled. What did he pull? What did he just throw away into the... Never mind. So now what do? We have a column of inputs. We have a column of outputs. We want a transfer function. We could look at any combination of these and produce a transfer function. We could say, oh, the input is a current. Well, maybe that's actually going to be applied to some machine, and that accelerates a shaft or a position. Or maybe somebody gives us a force in, and it gives us a current. We measure a current out. Or any of these possibilities. We might have a velocity, and maybe it gives us a voltage. Do you see the idea? You can mix and match. What do you want? Sorry. I kind of had a little too much caffeine, I think, before class. That's the possibility of combining. Let's look at an example. Let's get me back in to something that I'm not... Now everybody's going to be sorry they missed this lecture, aren't they? The video, yeah, it just lacks a little something. Let's look at an example. Suppose now we have v sub g of t series RLC circuit. We have a resistor, we have an inductor, and we have a capacitor. And we're in the time domain right now, so this, let's say, is the voltage across that capacitor. Here's the current through that series circuit. And just with those three labels, signal labels, we now have a couple of transfer functions identified. We could worry about the transfer function between this voltage source and this voltage across the capacitor. Or we could worry about the transfer function between this voltage source and this series current. There's two different transfer functions right now for one electrical circuit. Now you can go home and just be dreaming up all sorts of transfer functions. See what you're going to be doing this weekend? Isn't it going to be fun? And you can even start doing convolution with some of that if you want. So now what have we been talking about? Well, now this was maybe in the living room and you want to go into the kitchen, right? We want to use, instead of writing differential equations, let's immediately start working in the S domain and writing down algebraic equations involving this complex frequency variable S. To do that, let's now translate this into the S domain. And if we are interested in transfer functions, do we need to worry about what I spent the first half of the class doing? Do we need to worry about the initial conditions if we're dealing with transfer functions? No, we're just worrying about the dynamic behavior. So we're not going to incorporate the initial conditions into this S domain circuit, meaning now we can quickly say, well, here is V sub g of S. There's our resistor, there's our inductor, and there's our capacitor. And how do we label these in the S domain? What's the impedance of a resistor? It comes in unaltered, doesn't it? It's just R. Whatever it started with in the time domain, it's R in the S domain. For an inductor, What's its impedance? I'm going to say SL, but it's LS. Either one. You can push that. Those two commute. They have a long commute. I'm sorry. It's a math. SL. What about the impedance of a capacitor? 1 over SC. Now we have our impedances identified, and we can label the appropriate signals, Laplace transform quantities that we had in the time domain circuit. Here is now our capacitor voltage and our series current. Now, based on this circuit, what is I of S? Now you can just go back in time and say, oh, I'm sitting in 220. How would I analyze this if I just had 3 resistors in series? Ooh, wouldn't that be easy? Doesn't 220 seem easy now? But now those resistors are generalized to impedances. Now I want that current. I just say, oh, I is the voltage divided by that sum of those impedances. And you have the the expressions for those impedances. Now we know that I of S, the series current, is V sub G of S over the sum of the impedances in that circuit. Can it get any easier? There's your current. Boom. In a second order system. But now somebody says, yeah, but I wanted a transfer function. I wanted the transfer function I sub 1 of S, which is in fact the input I wanted to be V sub G of S. So I put that in the bottom. And I put my output in the numerator, and I want that to be the current, the series current. This is now my transfer function between the input, which is downstairs, the source, divided into the current I. Do you see how to find H sub 1 of S? You have it staring us right in the face up above. We just need I divided by V. So if I simply divided both sides by VG, those two cancel, and I now have I over V sub G is equal to 1 over R plus SL plus 1 over SC. Now, that looks a little bit odd, because now we have denominators in denominators because of these impedances. Meaning I have a 1 over SC in the denominator. Well, now we just need to rationalize things or get everything in a polynomial form, a polynomial in the denominator and a polynomial in the numerator, and I can do that by simply obtaining a common denominator downstairs Did I do that right? I just put everything in the denominator over SC. And that better be correct. And what happens now? Well, I can always multiply things by 1. And my 1 now, let me be SC over SC. Where this SC cancels, and now my transfer function, H sub 1 of S, which in fact was I of S over V sub G of S, is now 1 over, and let me order this from highest power S to lowest power S. I now have S squared times LC plus SRC plus 1. Oh. No wonder I had so much caffeine. I was trying not to fall asleep. I have the SC coming in that from my 1 that I multiplied it. Now is that better? I now have SC up top, and I have S squared LC plus SRC plus 1. What's the order of the denominator? What's the power, the highest power of S? Second. How many energy storage devices did you have? 2. So generically, if you don't have any special combinations of parameters or elements, circuit elements, you should see your denominator order being consistent with your energy storage elements in your circuit. And we can identify zeros and poles. The zeros are the values of S that cause the numerator to vanish. And they took away our tenths on them all, but our poles are the values of S that cause the denominator to vanish. If the denominator goes to 0, what happens to the whole H sub 1? It goes way up, doesn't it? That goes to infinity. That's the pole. The values of S that cause H sub 1 or any transfer function to go unbounded, those are the values of S that cause your denominator to vanish, and those are the poles. The values of S that cause your numerator to vanish are your, if you wanted to get technical, your finite zeros. All right, suppose somebody said, no, that's not the transfer function I wanted. I actually wanted H sub 2 of S, which was V sub C of S over V sub G of S. The capacitor's voltage over the supply voltage. But it's not going to be hard to find that transfer function because we already know the series current, I. And if we now know I, how do we find V sub C? It's Ohm's law, the generalization of Ohm's law. It's the impedance of the capacitor, which is 1 over SC, times that current I. That's V sub C of S. V sub C of S is now 1 over SC, which is the impedance of the capacitor, times I sub C of S. Well, an I sub C of S, since it's in series, is I of S. We didn't subscript that I, did we? So it's just I of S. And we knew what I of S was. I of S was V sub G of S over the sum of the impedances that were in series. And, wow, we have an SC in the denominator out front. We can just multiply that through to clear that 1 over SC in the tail end in the denominator. And we're left then with V sub G of S over SRC plus S squared LC plus 1. That's V sub C of S. And somebody said they wanted H sub 2 of S, which was V sub C of S over V sub G of S. And do you see how you can get that? We can divide out the V sub G of S in the right-hand side, and that gives us V sub C over V sub G on the left. And that now becomes, what I've done is I've just said, oh, actually this is now, those cancel, and I'm left with 1 over S squared LC plus SRC plus 1. And that's H sub 2 of S. That's the transfer function between that voltage source and the voltage across that capacitor. That's how that relationship, that's the dynamic, or that's the governing dynamics of that circuit from input voltage source to output voltage across the capacitor. That's its transfer function. And one thing that we will start focusing on, obviously, are these poles. And we have a we have a denominator polynomial here for h sub 2, and we have a denominator polynomial for h sub 1. And if you were playing a match game, you could see that those two, so if you were doing concentration or something and you turned over and you said, oh, here's the denominator, and it was this, you turned over the next card and it had the same denominator, you get that pair. Okay, there's your... Half of you don't even know what I'm trying to... But... that denominator polynomial is actually a characteristic of that circuit. We didn't change the circuit, did we? And the denominator is characteristic of that circuit. So you give me that circuit, it's going to have a particular denominator. And that's what we will call its characteristic polynomial. This characteristic polynomial is actually equal to the denominator polynomial. And I hope you could see that that was the same in h sub 1 of s and h sub 2 of s. That circuit you didn't change between h1 and h2. You just looked at different outputs, but they both had the same characteristic polynomial, or they shared the same denominator. That's one of several properties of a transfer function that I want to now list. First, linear, lumped, parameter circuits, in fact, yield rational transfer functions. Maybe I'm using some terms there that you didn't relate or associate with electric circuits. Lumped, maybe you were thinking oatmeal, lumpy oatmeal, but it also is lumped parameters. What do we mean by that? If I give you an R, that's a lumped parameter. I give you a C, that's a distinct element. I give you an inductor, a physical inductor, that's lumped. It's just one inductor value. Contrast that with a transmission line. Then the inductance is spread out. It's distributed across that transmission line. That's the contrast between lumped and distributed. Or, let me first say that lumped parameters you can sort of just think discrete components. Those are in the bin in the stockroom. Those are your discrete components, resistors, inductors. If you have discrete components, those are not the same as distributed components. meaning here with discrete components, our circuit elements are lumped values of R's, L's, and C's. And that will give us equations or matrices that are finite dimensional. The orders of our system, that denominator polynomial is fifth order. It's sixth order. It's finite dimensional. Contrast that with distributed components, which might be something you see in another class, ECE 381A, transmission lines. So transmission lines now have their characteristics, their properties uniformly distributed. You don't have a lumped value of an inductor, for example, and in fact, these might now correspond to partial differential equations or infinite dimensional systems. And aren't you glad that we're not working in that right column now? Because it might be a while if you're drawing an infinite dimensional circuit. No, but if you did it using lumped parameters, yes, you would have to include an infinite number of circuit elements. But here you could think of this giving rise to infinite dimensional analysis. We're not going there. We're going to stick with discrete components and lumped parameters. Those give rise to transfer functions that have polynomials in the denominator and polynomials in the numerator. That's what we're looking at, rational transfer functions. 2. We're listing properties. Transfer functions are obtained under zero initial conditions. We didn't need to worry about sources, current sources or series voltage sources in finding these transfer functions. 3, poles of these transfer functions of h of s govern the natural response or transient response of the system. For example, suppose that somebody gave you a transfer function, h of s, and you looked at that transfer function and you said, what could I maybe start to understand about this system? Let me look at the denominator and see what values of s cause it to vanish. Which values of s cause the denominator to go to 0? Those are the poles. So you're looking for poles. You're looking for poles, and that's going to give you information about your system, because that's going to tell you how your system will naturally behave when you initialize it with initial conditions or you kick it. That's how it naturally wants to move. Let's say that now somebody gives you a transfer function and they say, oh, this has, or you find that that system has poles at s equal to -1 and s equal to -6. What's the order of that system? Second. It has 2, and are these repeated or distinct poles? Distinct. My class is learning the average is high, if you're wanting to know. So now, what's the natural response? What's the structure of the natural response? If somebody walked up and kicked that system and it had poles at -1 and -6, how would it naturally want to shake? Let me just call that y of t. What would the output structure look like? Pardon? So now it's going to be decaying exponentials, isn't it? And the -1 and the -6 give us the modes, e to the minus t and e to the minus 6t. And if we're just looking at the structure, we don't need to know a and b. We could say y of t is a, e to the minus t. There's the first mode from pole s equal to -1. And our second mode is e to the minus 6t. That's how our system naturally wants to respond. Yes?
I might be wrong on this, but is it supposed to be e to the t?
Does that look right to everyone, I think is the question. Does this, if we had poles at -1 and -6, what are the modes associated with those poles? So now we have e to the st, don't we? We have e to the st, and s is -1. We have e to the minus t, and we have e to the st, s sub 2t, where s sub 2 is -6. If our poles were at -2 plus and minus j7, now what would our system naturally want to do if we excited it or energized its energy storage devices? -2 plus and minus j7. It's exponentially damped sines and cosines. What's the exponential damping? That's influenced by the real part, how far into the left half plane. That was the -2. It's e to the minus 2t. How does it oscillate? How does it shake? What's its damped frequency? That's the imaginary component. That's the 7. So you have e to the minus 2t times cosine 7t with, let's say, a coefficient of a plus b sine 7t. That's how that system would naturally want to shake or move. It all depends on the poles of your system. 4. The denominator polynomial, which we already said this one, but let me just repeat it as a property. The denominator polynomial, in fact, equals the characteristic polynomial. Five, a stable system, and that means if I put in a bounded input, I'm going to get a bounded output. If my x of t has a bounded signal, then if my system is stable, my y of t will be bounded. A stable system has all of its poles in the left half of the complex S-plane. In the left half S-plane. The poles have to have negative real parts. They're to the left of the imaginary axis. They're in the left half of the S-plane, and I might abbreviate that so that if we're texting, and I did appreciate the comment on some exams that said if we're texting, then we would do it LHP or something. So if we text, we're doing LHP, right? Then everyone knows, if you're in the know, if you've seen 320A, that that's referring to the left half plane. Oh, the system is stable. You could say my system has poles in the LHP. Now you apply a bounded input, it's going to give you a bounded output. And a passive RLC circuit, or let me say RLC network just to be even more general, produce stable or unstable transfer functions. If I give you an electric circuit and it's consisting of resistors, inductors, and capacitors, and I now excite that system with a bounded input, am I going to see a bounded output? Or is something going to go crazy and it's burning up? It's going unbounded. That resistor is dissipating all the energy. Those resistors are dissipating the energy in that circuit. If you energized all of those energy storage devices, the inductors and the capacitors, and you let it go, it's not going to go crazy on you, is it? Those resistors are going to dissipate that energy. So this was going to lead to a stable system has all of its poles in the left half plane. A passive RLC network has all of its poles in the LHP. Or a passive RLC network produces stable transfer functions. If you had an active circuit, op-amps, powered devices, that's not what we're saying. We said passive. Okay? 6. The zeros of H of S, H of S being a transfer function, are the roots of the numerator polynomial of the transfer function H of S. So it's important to clean up your numerator and denominator. If it's ratios of ratios, you want to essentially end up with a polynomial divided by another polynomial. Then the numerator polynomial, it has roots, and the zeros of that numerator polynomial we will call zeros. If the finite zeros, those are zeros that are in the bounded complex S-plane. If the finite zeros of a stable transfer function H of S, if the finite zeros are in the LHP, if you have all of your finite zeros, and we'll label those as open circles on our complex S-plane, if all of those open circles are also in the left half plane with all the x's will be poles. If the x's are in the left half plane, then the system, that H of S, is called minimum phase. Now if somebody is talking to you in your internship this summer and they say, well, this system's minimum phase, you're just going to be able to sit back and grin and say, I know what he's talking about or she's talking about. They're just saying that transfer function has all of its poles and zeros in the left half plane, in the LHP. Meaning, now if you had, and now you might be saying minimum phase, okay, I know what how it's defined, but where did that come from? Let me show you. This is fun. Well, maybe I shouldn't preface it that way. He says he finds that fun. Here's the S-plane. You'd be surprised. Here's the real value of S. Here's the imaginary value of S. And let's say that now you have poles that are at -2 plus and minus J1. There's J1, here's -2, so we have a pole there and a pole there. And let's say that we have a 0 at -1. In that case, our h of s, our transfer function, has a 0 at s plus 1, and it has a denominator that can be written like that. And from the pole 0 diagram, you really can't say what the gain is, so let's just say it's an A1. This is now a minimum phase system. Contrast that with a non-minimum phase system. Suppose instead of the 0 being at -1, it's out here at +1. That's now a minimum phase system. Suppose we were looking at the phase of this minimum phase 0 at J1. There would be its angle. But if we looked at the angle associated with that, do you see that the red angle is bigger than the blue angle? They would both have the same magnitude response, but the red angle, or the red singularity, the 0 in the right half plane, has a much bigger angle. It's non-minimum phase. It can't be a minimum phase. So we'll pick up with that and frequency response. Man, we have so much to go. It's going to be exciting. See you next week.